Good afternoon, dear Scientific Council, dear ladies and gentlemen, dear guests on YouTube, if there are any. Let me present you my professor's lecture, which is entitled Optimal Inverse Design in Electromagnetism and its Effective Implementation. And actually, I would like to start this talk with a quiz. There are three pictures, one bridge, one plane, and one cell phone. And can you guess what they have as a common characteristic here? Well, this should not be a torture, so I can tell you my opinion. Actually, all of them were considered at their time being optimally designed for a given parameters. That's the Troja Bridge, famous spy plane, and cell phone. And this actually brings us to the topic of this presentation. We will discuss what is optimal design, how to achieve it, and what are the properties, and so on. And actually, this is a very vital topic in electromagnetism because, especially at this faculty, we all know that electromagnetism is everywhere, so as the electromagnetic devices. Just to look around yourself, cell phones, laptops, beamers, screens, everything is electronics, and with the spectrum being occupied more and more with the limited sources and so on, this is a very important topic, how to make the devices better if we are witnessing higher and higher requirements on their performance. We want all devices smaller, data throughputs should be higher, we should use more economical materials, and so on. Just here on the right, you can see that the number of connected devices is like skyrocketing. It's actually an exponential curve. And so, again, how to make designs better? And this is the important question here, and I would like to take you on the expedition through the modern electromagnetism and try to address this question. So what does it mean better? How we can address this problem? And then, is it possible to somehow solve or at least attack this problem in some reasonable way? So that's the content of my talk. Here you can see the outline. I will not spend much time here, but definitely first we should somehow define what is here of interest, which is the term inverse design. That I will do first. Then I will discuss what are the degrees of freedom, I mean optimization variables we can play with. And then I will introduce our original approach to this problem, which is based on something called exact analysis. Then I would like to somehow convince you that it works on a couple of showcases, nice examples. And then, since this should also partly be about the future, I believe, I would like to share some vision with you about the future devices which are yet coming. So that's the content of this talk, and on the right you can see some really first showcase of this lecture. It's a moving picture, and what is there is actually a synthesis of some antenna starting from random seed. It's nothing, it's just a crab. But at the end you have something which has reasonable performance in electromagnetism. Of course, there is still a lot of labor regularizing and so on. I will touch all these points. So that's the plan for the following 27 minutes. And let's start with inverse design. What does it mean? To explain that, we have to touch two important terms, analysis and synthesis. And analysis is the simpler one. Analysis is basically everything we do every day. Basically, if you have a device, cell phone, or some motor, or some plane, and you would like to assess its performance, you typically draw that design in some powerful electromagnetic or in mechanical simulator, and you run the simulation, and you get your numbers, how it performs. That's really mastered. But what is the problem is if you have the opposite task. Imagine that your boss enters your office and asks you to design a new device, having efficiency better than something, being smaller than something, made of this material. You have three numbers. At the end, there should be a device. So that's a much more complicated task. It turns out at a certain moment of this talk that it's NP hard. And you should see the differences. We should really differentiate between what is already mastered and we use every day, and what is considered to be unsolved in principle, what we can at least try to address this problem somehow. Maybe to visualize it, because maybe some of you have more visual kind of memory and imagination. Basically, this is an interplay of two domains. One domain is where the material, excitation, where the physics really sits, I mean, what we can somehow shape, cut, and so on. On the right, there is the performance domain. We can definitely measure efficiency, directivity, weight of the device. We have also other considerations, like we would like definitely to design something which is manufacturing friendly, so without some tiny protrusions and so on. And so the way to right is analysis, and the way to left is synthesis, and that's considered to be unsolved. Why? There are some difficulties. And I wanted to somehow demonstrate them on a couple of questions. You can try to answer them on your own. Can the functionality of any device be chosen arbitrary? Well, probably it cannot. We cannot have higher efficiency than 100% or device more than something. There are some fundamental bounds we cannot cross. Then, is it a hypothetical solution unique? Well, I can tell you it's not unique at all. We live in very complicated solution space where he has, in principle, infinitely many good solutions, and you will see why. And the last one is quite engineering question, but it's a very important one. If you know the functionality of your device only approximately, as is always the case, rounding error, discretization, measurement, and so on, is then the corresponding solution close to the exact one? Not at all. That's not true. So we have many problems, and they are even amplified by the fact that, of course, we have to numerical model things in our computers. That means that we have to discretize them. For example, here, to make it simpler, two triangles. So we can think of operating over these triangles in some, for the beginning, some dummy way, switching them on, off, and on and off, sorry. But in that case, you quickly realize that having more and more triangles, the number of unique solutions explores. It's impossible to solve it by some exhaustive search or some genetic algorithm, something like that. Because typically, even this solution is not enough to have a sound physics behind it. You need much denser, much finer mesh to really solve it appropriately. To illustrate it on one example, here you have two basic antennas. We teach these antennas to our students, a dipole and a loop. If you see carefully, the only difference is this tiny pixel in the middle. Yet, the electromagnetic behavior is completely different, for example, in terms of the input impedance. So you can see that if we start to run some algorithm which is performing the shape, doing some clever things, this is problem, because the problem is sensitive, non-unique, and so on. So speaking more specifically, this is really the mathematical prescription of the problem, and take the symbols, basically, that they are something. I will explain only some of them. A and B's are some matrices. We can pre-calculate them, construct them, and they serve to evaluate the performance of our device. I is a current flowing in that region we would like to optimize, and the important part is actually this last constraint. You can see that it's some kind of constitutive relation you have to always satisfy. But unfortunately, to satisfy it and plug the current back into the equation, every step you have to solve this. I mean to invert the matrix Z, and the matrix Z that describes our system. And that matrix is huge. It is in thousands by thousands, maybe even bigger. So imagine to invert this again and again and again and move in that crazy solution space. Normally, you cannot find anything. So this is a problem of discrete optimization, obviously serving from the curse of dimensionality with all the consequences. And so how to start at least to study this problem? Here are two shapes. They are the same ones. And here I would like to demonstrate that you can pick different optimization variables. Imagine that this diamond-type shape is discretized into triangles. That's on the left. On the right, there are the basis functions. It's a detail, but important detail, that within our modeling of the physical problem, we need to set up some basis functions. And they are here typically aligned with every inner edge. One possibility would be to start to perturb the triangle, so really to perturb the material. Think of that as follows. Within that triangle, if is it yellow, the material is there. It's made of conductor. If is it white, it's not. It's a vacuum. But this is a problem, because if you remove one triangle, typically in our matrix, in matrix Z I was showing, you have to invert. You have to perturb many of the columns and rows at once. So at the end of the day, you have to really do the inversion again, the full matrix inversion. But what if, and this is our original idea, what if you do something crazy? Instead of that, you will perturb one of the basis functions. So you don't change the geometry or the geometry of that obstacle. You can see that material is still everywhere. It's still yellowish object. But In that case, if you switch on or off just one basis function, you perturb only one column and one row of your matrix. And well, this is very well open to some rank 1 update of the matrix. For example, famous Sherman-Morrison-Woodbury identity, which we actually utilize here. And yeah, then it's extremely fast, because in fact, you don't invert the matrix. It's ON, it's linear operation, and you can think of that here at this faculty as that we connect a resistor in series with that basis function, which is infinitely large value of resistivity. So effectively, we cut infinitely thin slot. I will try to explain that on the next slide as well. So that's the original idea for which I received a Junior Star project of the Czech Foundation Agency, and we are now working on that. And basically, we decided somehow to live with the MP hardness of the problem. We cannot do anything with that, that's obvious fact. But instead, we will try to solve the problem as many times as possible, hoping that in that large solution space, we can find some promising candidate. And we will do it in local, gradient-based manner. So we fix the discretization. So the discretization, the triangles are fixed. So as the excitation. We precalculate the Z matrix only once. That's kept. And we only reuse it again and again. And the important step is that when you solve this equation again and again, you do this inversion. You do this inversion only for potential shapes, which are only rank 1 different to the initial shape. So you basically study only the smallest possible perturbations of the shape, but you do it discretely. So it's basically a sum nearest neighbor algorithm over Hamming distance 1. And again, to visualize it, imagine this is the initial shape at a certain stage of the problem. And the edge in the middle is fixed. That's the black one. There is a feeding. We cannot touch it. The red ones, they are definitely a subject of a possible shape optimization. So we can remove one of them here or remove another one. But also we have 4 possible additions. We can add one here, on instead one there, or over there, or you can see that there is also one edit. All of these shapes are just rank 1 perturbations of the original one, and therefore take for granted that we can solve it in really very, very small computational time with almost no computational burden. With that, we can set up topology sensitivity. Well, this is here, and this is nothing else than to just subtract the performance of the initial shape from all the performances of the perturbed shapes. Okay, nothing more. And with that, well, then here you can see a visualization of the algorithm, how it works. Then really, it's an iterative algorithm. So you start with some particle shape. Yellow is again a material. Gray here is a vacuum. And at every stage, you have a topology sensitivity information about every inner edge. Positive numbers means that you do nothing, you keep that edge there. Negative number means that it would be good to remove that edge, because then the behavior in the studied performance metric is better. What we do is here that basically the simplest actually what you can do is to follow some greedy algorithm, and we always perturb only the worst one. So that's the algorithm. Here, it's something about its implementation. When we start, we have to precalculate all the operators. As I mentioned, they are rather big. We do it on GPU to make it fast. Then there is the local algorithm. So we start with some particle shape. Well, just take some initial seed. And very quickly, we go to the local minima. So we find a locally optimal shape. But of course, there are many local minima, as I said at the beginning. So over that, there is also some global step, which takes these locally optimal shapes and perturb them somehow, mix them, shuffle them, do something with them. So that global step is some genetic algorithm. But that's not the important point. Important point is what sits there, and that's our local algorithm, which is super fast, because it's also fully vectorized. And then the global one runs in some parallelism on all the CPUs you have. So that algorithm is pretty fast, I would say, and everything is implemented in Atom. And speaking of Atom, that's our tool we developed. And you can see that we were pretty successful in disseminating this tool around the globe. This tool is owned by this faculty. And we were also able to to sold a couple of licenses to companies like Sandia Laboratories and so on. Okay, now actually notice that now we are under negotiation with Amazon for some kickoff project, and they want something to implement from our side as well. So this is not only theory, it can be really applied, and it can be after also commercialized in some reasonable way. Okay, now I promised a couple of examples, so there will be here. First of all, what can be the most broadband antenna? Let's start with this spherical shell. So it's a ball, it's discretized into triangles, and this is the result. It's quite ugly. The current on that is this one. But even the fact that it's quite ugly, it is only 27% from the fundamental bound, which is somehow preset by physics. It cannot be then done better. And by the way, it's far the best design which can be found in the literature, at least according to this metric. Of course, it took 46 hours to optimize that, so quite a long simulation. But notice this number. Within that 46 hours, we were able to investigate and evaluate 620 millions of antennas, which makes 4,000 antennas per second. If you open your electromagnetic simulator and draw this there, it will take minutes to calculate one antenna. Okay, but you maybe notice that the shape is not very regular. So what we do as the post-processing step is that we regularize the shape. Basically, it's based on graph theory. You have two graphs or maps. One is the material elements, triangles made of material. It could be copper, silver, whatever. And you have the basis functions. That's the connectivity graph, how the material pieces are connected. And with this, you can construct incidence matrix and then set up some regularity metrics. And this is nothing else than a product of the incidence matrix and some operations over it, evaluated in Boolean sense. So it costs nothing. And then you can take whatever shape you like, and you can evaluate its regularity. And then in the algorithm, we combine the regularity aspects, the physical aspects, and we can really get shapes which are not only optimal in the physical performance, but also, as you will see on the next example, which are very regular. So the second example out of 3 is a spherical cloak. Actually, it's an idea which goes back to these 2 famous papers. What is it about? You have some object you would like to hide. There is some incident field, and the idea is that you construct something around that object which basically bends the electromagnetic fields so that they are again constructed after that object. So effectively, you hide that object. Okay, so we implemented some numerical method. This is our setup. The object in the middle has to be hidden. And the hatched area is where we can design whatever we want out of some silica material. This is the result. And notice that the response of the inner object we would like to hide, the electromagnetic response has been reduced by 2 orders. So effectively, we somehow hide that object. And with that, I would like also to demonstrate that we have some iterative scheme with our algorithm, which starts with a rather poor mesh, finds optimal solution, translates it to a finer mesh, and again. So at the end of the day, we can deal with 10,000s of optimization unknowns in a reasonable time. And again, it's thanks to the local gradient-based algorithm, which is at the on the very bottom layer of this. And here you can please your eyes with some plane wave hitting the object. Then it goes around the object which is in the middle, and then you can see that the wavefront is again almost perfectly constructed on the right, and the plane wave continues almost non-disturbed. Last example here, lenses, classical problem. To construct lens which has the highest possible focusing efficiency depending on the focal length. And again, the solid line is a bound that's dictated by the physics. Any hypothetical device cannot be better. These marks, the circle marks, are our designs, and you can see how they look like. I would consider them as beautiful shapes. They are very smooth. They are distributing the field into locations where you need it to focus it again, and into the focal point, and that's what the algorithm does. But before I go to the conclusion of my talk, I would like to share the idea I promised to share with you, some future vision about all this, where I believe that the algorithm can really be in lead. Well, it's about wave computers. They are kind of analog computers, but constructed in a very fancy way. Probably you also know that large electricity nowadays is really spent to train and evaluate artificial intelligence, and it will be even worse in the future. And actually, many of the training is just adding single precision numbers together again and again, and doing that basically a billion of times, still the same operation again and again. So quite clever guys publishing in Nature or Science or Nature Communication, they propose that maybe in the future this could be solved by some optical crystal where you illuminate it with a laser, and that laser already carries the information. It could be, for example, some picture. And within the crystal, you can perform then first derivative, second derivative, which is edge detection. You can maybe do some integration, summation of the numbers, and so on. So that's the idea, definitely not brand new. It goes back to the 60s, but now maybe we have the technology, and you can see just a few papers from recent years. So at my department, we constructed this prototype, just to input to output ports, which is basically used for this, where you can manipulate with the blocks of Teflon, and you can play with simple algebraic operations like here. What is different here, as to two examples I was showing before, is that before you optimize for one metric, focusing efficiency, bandwidth, but now you have to synthesize matrix. Matrix doing that operation like here. For example, if you want to add two numbers together, you need to synthesize a matrix. This device has to perform this algebraic operation. This is complicated, but I believe that it's very well feasible with our algorithm, because it's immune to many imperfections of other algorithms which are known and used, like topology optimization, genetic algorithms, and so on. This is something more, and I believe more powerful. So with that, this brings me almost to the end of my talk, but not quite the end. So what you have seen today is a memetic algorithm. It's a powerful one. It can deal with whatever electromagnetic metrics you are able to find and define a performance metric for it. It's complete in-house framework. So whatever you have seen, all data, all figures, all pictures, all equations, everything is in-house. And also provided on our webpage. You can buy it. But more than the past, I would like to focus, actually, with high focusing efficiency, to the future. So I think that there are many open questions, like what is the true link between the physics and the topology? Now we have some operators to address that with the graph theory, operators which are perfectly compatible with the physics. We can add them together and find, for example, geometry modes and other things I hadn't time to discuss. Obviously, we are able to generate a huge data sets. Those data sets are so huge that we cannot even store them on our hard drives. We just mine data about physics. And maybe this would be open to some interpretation with modern artificial intelligence tools. And my guess is that it can give more questions than answers about the similarity of different problems, about the structure of the solution space, and so on. Clearly, the future is synthesis of multifunctional devices. For example, think of reconfigurable intelligent surfaces. They are coming. They will be everywhere in 10 or 20 years with 6G. Those will be walls, clever walls, which will bend the signal, reflect the signal. And design such things requires really a multifunctional optimization. And finally, the holy grail for me is somehow to return the computational science back to the physics so that we will be able to perform computational tasks over the matter, really, with the wave phenomena. So it will be not discrete lumped elements like transistors, but there will be really a solid piece of photonic crystals, and we will be able to shape the light. So something will be possible to calculate on that level very fast. It's very speculative, but there are papers appearing in this field right now. And of course, last but not least, I would like to promote this field worldwide. And for that, I have a good news that it is last week that our new proposal to the European School of Antennas course on fundamental bounds and inverse design with my close colleague, Mats Gustafsson from the university, has been accepted by the board. So next year, it will be organized for the first time. Then let me thank to my family, to my friends, to my colleagues. And with that, I have the last slide here. I have been asked for that slide by Milan specifically, that I should also provide some, I don't know how to translate it, some kind of guideline or something like that. So consider this as kind of experiment. So there are 5 points, which I believe somehow characterize me. I personally believe that if you have a choice between quality and quantity, it should be always quality, as I hope demonstrated here by some metrics. Then I believe that small teams have the place here, and they are very prolific and very efficient. So this is more a message for the decision makers, but there is a beautiful paper in Nature about it, that really all the disturbing technologies are coming from smaller teams usually. So that's open to the discussion, but I believe that that somehow characterizes me and my colleagues. We have an extensive net of collaborations. I would like to maintain it and expand it further. Finally, be active in community. And last point is that I personally like, as often as possible, to step outside of the electromagnetism, because then you can find the true inspiration and analogy. And actually, that was the case of the exact analysis algorithm. It's known for 10 years in civil engineering and mechanics. So we took that idea and bring it into electromagnetism. And with that, let me thank you all for your attention and also for the chance to stand here and talk about my work. So thank you. And here is the slide. You are more or less expecting that it will be there.
Miloslav, thank you very much for a very interesting and illustrative lecture. And now I open the general discussion to the topic of the lecture. And I'm asking for the questions. Professor Matas?
Okay, so I have like 6 questions, but I'll reduce it and we'll do something for the second round. Maybe the first comment would be like your last slide with number 1. You know, as scientists, I rarely say always. I'm thinking quality always beats quantity. I'm thinking about the Ukrainian war, and let's hope. Yeah? So yeah, sometimes quantity beats quality, for sure.
Yeah.
Okay, but let's forget it.
I have a bit problem to hear you here, actually, clearly, because the sound is like bouncing there and back. So
okay, maybe you can go forward.
Yeah.
Maybe the first comment is be careful as a professor with the word always. If we look at Ukraine, maybe quantity sometimes on the Russian side can beat quality. It's not always the case, so I would be careful with always. Coming back to the real questions, you had this design of this hiding of the sphere. Now, I was thinking you do it in 2D. This solution must not the optimal solution be rotational symmetric, and you can do it in 1D everything?
Not necessarily. Symmetry plays definitely a role there. And if you have, if it's not shown there, but if you have some arrangement which is symmetrical, then we typically optimize only in half of the shade.
But here it's rotationally symmetric, like in polar coordinates, because if it's not symmetric, it will behave differently from different angles. Okay.
Yeah. Let me go back. Yes. That's right. That's perfectly right. And good observation. I hope that you mean this one.
Yes, exactly. So
and the thing is that the incident plane wave goes from specific angle. So we are able to hide that object only from that angle. But it's even worse, only for a particle frequency.
Okay, I was over-optimistic because I know that somehow some gadgets like codes that hide do exist, and this was like one that, okay, fine, then explains it. Now, have you heard about something like simulated annealing?
Oh, yeah.
So is this applicable here?
Yeah.
Which means like accepting certain worse solution with certain probability, and it might lead to...
Yeah, it is. And in fact, in many commercial solvers, that's one of the options how to optimize your device, like genetic algorithms, particle swarm, but they all are, a bit fuzzy. So you get something, but this is definitely better. I have some comparison
and
later on.
Last question, coming to the slide 5. Why?
5?
5. Like this. Like, this is 19.
Yeah, sorry,
This is 15.
Yeah, I see.
Okay, now you define here, now what I didn't understand, I thought that synthesis in common use is very similar to design. You design something, you synthesize something. Why is synthesis inverse design?
Yeah, well, this is a great question. It's actually about how you look at the problem, from what view angle you look at the problem, but we will probably agree with each other that if there is some simulator which evaluates your performance metric, it has to be always there. So you typically try to shape the structure and ask about the performance. And, well, designers do this all the time, every day. So this is the design procedure.
Yeah, maybe not from performance, from requirements to generating something that will be evaluated.
Yeah, and with the inverse design, I only wanted to highlight that it would be great to have some design procedure which goes really directly there. Our algorithm is not doing that. Our algorithm is design algorithm, still does the things for many antennas.
Okay, so yeah, because maybe you want to say inverse approach to design or something like that, rather than...
Yeah, it's a synonym, yeah.
Thank you. Professor Hasdra.
Well, I have a question. I guess many people in this room dealt in their life in the synthesis of the complex system. If you take ICs, so they have such a number of elements as a number of electromagnetic devices you show that they are in the whole world. So as I look to your work, you have the advantage that your problem is quite, in apostrophe, simple. Because, well, you use the equations, the Maxwell equations, ideal material. And usually in the practice, we have to deal with a different material, different problems, and so on. So there are different approaches to the synthesis, analysis, different levels of abstractions which are used, etc. So have you tried to use the approaches where you use a different level of abstraction, of the description, and of the approaches? Well, that was a simulated annealing. Mm-hmm. Yeah, that's usually used where you are interconnecting millions of particles together, and it's quite simple. So have you found some analogy between your approach and the approaches which are usually used in the design of complex devices? Have you looked at it? Yeah. So.
Yeah. Of course, I hadn't time to put it directly into my lecture. But I was sure that someone will ask. So there are many overlays. Sorry for that. But I have even some comparison here, just to put something on the screen while I will answer that. So there is really here. So yes, we tried extensively with many different algorithms, and the thing is that basically, actually, this is a good slide to start with. All the algorithms are either local or global. Global, genetics, and so on. You basically try something and try again. Local, that's for example, topology optimization. You know the derivative, you follow the derivative. But both these approaches, you can see there are two results. State of the art for two antennas. They look almost like our algorithm, except of the right one for the global method. It takes enormous time because it's a global. While the local ones, and they exist, there are many like topology optimization based on adjoint formulation. They in electromagnetism may have some problems with the sensitivity of the problem. While these local algorithms are phenomenal for example, in civil engineering. They are state-of-the-art. Really, bridges or components of cars are designed with that, and it's commercialized. It's in hyperworks. You can deal with that. In electromagnetism, it's not the case. And for example, the annealing is one of the methods, which is also in all the commercial simulators. But you typically get something. And really, it's open to some comparison. Here are three methods. Our is the red one, and the detail is in the top pane. And However, I would like to return to the very beginning of your question, because, of course, the real design problem is much more complicated. It's more colorful than just playing with pixels. But this serves to give you some idea of how radically new device can look like. And everyone in the field uses this just for the first hint. So you look, for example, at the helix antenna I was showing as the first example, and you know that, well, maybe the antenna should be like helix. But you are not sure, maybe it's a helix, it's two-arm helix, maybe it's a loxodrome, but you have some hint quite quickly where to start identifying your device. Because this should be used mainly for radically new devices where you don't know. This is not to design dipoles. We have libraries for that, tables for that, software for that.
Professor Kratochvíl.
I would like to ask, you said that you are solving an NP-hard problem, so there's a large solution space, and if I understand correctly, your method is looking at some local changes. So in the highly exponential space, solution space, you check only some of the solutions. That's the principle. And now my question is, you compared the efficiency of your algorithm saying 20% away, 27% away from a theoretical bound coming from physics. Mm-hmm. I would be interested if you can compare it in some cases with the exact optimum, which would take weeks or months or I don't know how long to compute, but how far you would be from the exact optimum, not from the theoretical bound, or how far is the exact optimum from the theoretical physics bound and so on?
Yeah. Thank you for this question. It goes to the point. The bound, the solid line here we are comparing with, it does not give you the design. It has been actually calculated slightly differently. If you remember the prescription of my problem, and I will simplify it. So there are some constraints, right? And there was this one, which makes it NP-hard. The fundamental bound, the solid one, is evaluated if you skip this constraint. You solve only this quadratic problem, which can be easily solved. It's really a convex problem. And that's the solid line. But since this constraint is not fulfilled, it means that for the solid line, you don't know the designs. Maybe they don't exist. So that solid bound is maybe not tight bound. And we would like to compare this with other designs or with the best design. But the problem is that we don't know that design. This is the best what we have. And by the way, these points are probably closest in the literature what we are so far. So we cannot compare. What we can compare is, for example, shown here. This is the lens on the right. And here we compare with the classical design. So with a really lens like this one. And then we can evaluate that we are by 21% better. But really a difficult point is that we are looking for something which we don't know how it looks like. So that's the reason why, for example, our AI algorithms fail here, because you don't have the training data. Maybe it can be done in a clever way, that's for sure. But at least papers now being in transactions of antennas, they are kind of unsuccessful in that. We don't know what is the ground truth. If I satisfied you with this answer, at least partly.
Professor Matas.
So somehow, a couple of times you stressed unique solution. Do you really need uniqueness here? Who cares? Like maybe, for instance, in training of deep networks, maybe the success is due to the fact there is a really huge space of almost identical local minima. I don't care. Yeah. So.
Yeah. Sorry.
So why do you talk about uniqueness? If you get your antenna, which is almost optimal. And there might be myriad. Actually, it might be the uniqueness might not be even feasible because you can have a huge number of almost identical ones, which even enumerating is not feasible.
I agree only partly, because first the fact that it's highly that the problem has many solutions indicates its complexity, but that's academic discussion. More important is that if you have many possible solutions, as a good engineer, you would like to select the solution, which also is manufacturable friendly, made of the most regular materials, and so.
Yeah,
so
this I expected, but this is, you have additional constraints that you really did not express in the mathematical formulation, and then you would choose by adding these other constraints.
Yeah, but if I add all these constraints there, I make the problem even more difficult to do. So better is to explore as many as possible and then to look as an engineer at some Pareto and pick the best one, my point of view.
Okay, thank you.
Maybe I have one question. Miroslav, you are an excellent theoretician. Did you also consider on practical aspects of your optimal design? For example, this spherical cloak, if we may have a look at it, there maybe, I mean this cloak, this spherical cloak, there are plenty of small, tiny parts of the dielectric. If you remove them to be able to manufacture the design, how the performance will change compared to this optimal design?
I don't know on this. I don't know with this example specifically. My guess is that they can be removed again with some filter or something like that. It's not done here. But what we can do is, and yeah, I will maybe move further to my slides because I always get this question somewhere. So I also prepared a slide here. So what you can do instead is that from the beginning, you set up the optimization problem in some multi-criteria way so that the regularity, the number of isolated islands, is one of the optimized metric. And then you can get more Pareto fronts. Look at the blue one. It's definitely better than Q. Q is the optimized metric, right? It's better. It dominates the red one. But if you look at the shapes, they are nonsense. To be honest, nonsense. That's just a game, computer game. But if you impose some regularity metrics, as I was showing, you can get more regular shapes. And one of the regularity metrics we have is that you can also punish all the isolated islands there. And then you see there is none here. These two structures, they are not suffering from that problem. But of course, as you would expect, you pay in physical performance. Because you want regularity, also, not only physics. But with respect to the practical aspects, I don't even have access to my laboratories at my department, so I'm not a very practical guy.
Maybe you could include some practical constraint on manufacturability in your design. Thank you very much. And do we have any other questions? So if no, thank you very much, Miroslav, for the lecture, and I also thank the audience for putting a question and for listening. And I close this discussion session.